So, sea ice prediction network south. A bit of motivation first to start with. That's a figure we haven't seen much, I think, so far. There's a bit of echo, no? So, the figure shows the monthly departures of sea ice sextant in the southern hemisphere from the long-term climatology month by month since the satellite record began in 1979. And the story is like this. Up to the middle of the 2000s, the situation was quite quiet with sea ice anomalies that looked a bit like white noise, let's say. But since then, the situation has changed a lot. So if you look at these anomalies, you have had basically two phases from 2007 to 2014, 15, a positive mode where, so meaning more cold conditions probably, where you have longer-lived anomalies until 2014, and then you have a sort of switch of sign in the austral spring 2015-16 associated to a strong El Nino event, and since then the negative value of anomalies have persisted. And so the question is, what's going on there? It looks like the stationarity of the time series is changing, so the persistence seems to be longer, the variance seems to increase, and the point I want to make is that we are currently in a phase where we might have actually a lot of prospects for skillful predictions because of these anomalies that are longer lived than they used to be in the first part of the satellite record. There's at the same time a lot of interest in southern hemisphere touristic activities, and so sea ice information is more urgent than ever. There's, for example, this estimated 53% increase in touristic activities compared to some averages before that. And so the goal of SIPN-South, which is a YOP Southern Hemisphere endorsed project, is to try to identify all the existing efforts for sea ice prediction in the Southern Hemisphere with a focus on the summer, to assess the skill of those systems, and then to address the question of the value of the forecast. Even if the systems are skillful, are we able to extract some useful information from the user point of view? But before that, maybe it's important to ask the question whether there is some predictability in the sea ice at all, given that it's almost entirely seasonal, as you probably know. And for that, I won't be too long on that one, but I will review the few studies that looked at this question. I think the very first paper who looked at the question of predictability of sea ice in the Southern Hemisphere was a study by Marika Holland and colleagues, and Ed, who is probably with us today. They looked at a perfect model ensemble simulation, so you have a model that you integrate, and then you restart the model from initial conditions, you perturb the initial conditions, and you measure how long it takes for the ensemble initialized from its own initial conditions to go back to the climatological distribution. And they estimated that the sea ice had some predictability, mostly thanks to the advection by the ocean of the surface conditions that could be stored in the mixed layer or even below, and then re-emerge the season after that. There have been a couple of other papers. I think I won't go through them for the sake of time, but the mechanisms were always the same, and the bottom line is that, yes, there is, at least theoretically speaking, some predictability in the sea ice system, and that's associated with couplings between the sea ice and between the ocean. So let's go to the point of SIPN-South. What we do every year now, and we've been doing that for 5 years, is that we start by issuing a call in November. And the call is, well, very open, so we distribute that on the social media, on mailing lists, etc. We just ask people to submit at least information about sea ice area integrated around the whole Antarctic continent, so that's a circumpolar sea ice area, but they can also submit the regional sea ice area, the sea ice concentration, and the sea ice volume if they like. We ask people to provide daily output, and then the simulations are submitted, we analyze them, We also allow for groups to submit ensemble forecasts if they are uncertain about certain aspects of their own forecast system, so they can use different initial conditions or different parameters in their model. Then we wait that we have observations, and we do some post-processing. We verify how good the forecasts were, and we do some sort of post-season reports. What kind of contributions do we get in there? Well, it's half and half coupled process-based climate dynamical models. And sometimes these models are actually ocean sea ice models forced by atmospheric reanalysis. That's the case of our contribution. That's the one at the bottom. But we also have a lot of statistical contributions. And by statistical, I mean methods that employ data mining or training any sort of statistical models based on past data, and that extrapolate the rules into the future to get estimates of what could be the state of the sea ice. So statistical means any sort of machine learning approach you like, from regression to a very complex neural network or deep learning approaches. It's all in that category. Is there skill? So the first thing that we look at is usually the integrated circumpolar sea ice area. That's the one that for which we have the most contributions, because that's the one that everyone is obligated to submit. And as you can see, there is skill in the sense that observations in February and the forecast, they cluster together. So the forecast here, they bracket the observations, but you see that this is at the expense of a lot of compensation of errors. Especially all the dynamical models that are indicated by a small d here, but these are all dynamical models. They tend to start biased high, and then they compensate this positive bias by producing excessive melt rates in the melting season, so that they come up like a flower right on the observations at the month of February. And the reason why there is this positive bias is not so clear to us at the moment, but it looks like it's a recurrent feature in many dynamical models that retain the winter sea ice extend way too long into the season, and then they start melting way too late, and then they melt a lot to catch up with the observations. The second thing that we look at is whether the dispersion properties of these forecasts are okay. This graph shows, for each line shows a forecast that we received for the 2022 exercise, so that was the exercise of last year. And you can see that you have multiple models, multiple predictions from different groups, and these are the observations for the month of February 2022. You can realize that there are some groups that are totally off the observation. So these ones, for example, have a big bias and also are quite spread out. Then there are some groups that are well spread, way too spread, but they bracket the observations, right? And then you have some groups that are more confident, but they have also a small bias. So we want to penalize, in a way, those models that are either highly biased or that have flat distribution in terms of sea ice area, because it's not informative in terms of usability of the information. So for that, there is a very nice and convenient forecast verification metric that maybe some of you know. It's called the continuous rank probability score. The idea is that if you have the PDF of a forecast and you have some observation, you take the cumulative distribution function of your forecast, and you would measure the area that is sitting in between that curve and the observation. And if you have a bias, then your CDF will be lying here, and you will have a lot of area because it's way to left or way to right. And if you have a flat forecast, then you will also have a lot of area because of the fact that it's flat. So it's a metric that, with one single number, penalizes both the biased model and the over-dispersive models. So we applied that metric, and the good surprise, so less means better. The good surprise was that there are actually a good number of forecasts that are better than a climatological forecast. And the climatological forecast is just consisting of all the sea ice areas from previous years that we take as a reference, as a benchmark. And so what that means is that In the southern hemisphere, when we look at the predictions, it's more useful to look at these models than climatology, at least when we try to predict the situation of last year. The reason could be exactly what I was explaining at the beginning, is that climatology is no longer representative of the current state of the system, because we are currently in such low conditions. So it could really mean that there is some added value in terms of skill for using models that take into account the actual state of the system. We also look at the distribution of the SIPN-South forecast as a group. And this is each time a different year of prediction, and you see that for the Southern Ocean, the observations are always contained in the whisker plots provided by all the SIPN-South forecasts. So that's a good news, and we wanted to test whether that was due to compensation of errors or was it just a real skill. So we produced the same graph by sector in the Weddell Sea, the Indian Sea, etc. And all sectors are doing pretty much okay except one in the Ross Sea, where there is a systematic overestimation of the sea ice area in those forecasts compared to the observations. And it turns out that this sector is actually pretty difficult to forecast for reasons that I can detail, but we have a few hypotheses there. Finally, and I think I will close there, is there value in the forecast? I would say not yet. This is the best that we can issue at the moment. It's an example of maps that we can produce when we have multiple ensemble members. It's called the probability of sea ice presence. So if you have, say, 50 ensemble members, you can count the proportion of them that simulate more than 15% of sea ice in terms of concentration, and then you would report that probability on a map. For me, it looks like there is information there, but we realize that it's way too coarse-grained. It's not refined enough for people to use it actually if they need to plan a travel to Antarctica, because a lot of dynamics happen at the coastline that is not represented in those models. And plus, there's also a lot of training to be done in how to interpret probabilities for users that are not trained to ingest that kind of information. The project is on GitHub, so you're welcome to make your own analysis. And we are also running a special forecast for the last targeted, the special observing period of the UP that started on 1st of May and is ending tomorrow, or the day after tomorrow. So you'll find out more about the skill also for other seasons than the summer. I think I'll leave it there, and thank you very much.
Any question from the audience?
Go for one. Thank you for the talk, François. Could you think maybe the predictive skill now in the Southern Ocean can be somewhat of a proxy or indicative of our predictive capacity in the Arctic in the future, where the ice is more seasonal? Because now it's a little bit more, has a seasonal characteristic in the Southern Ocean. So can we make such exercise, just like thought exercise of, is it a good proxy for the future, or is this regionally so different that it's not really valid as a sort of like, image? Or
Maybe Bruno wants to answer. Well, that's interesting, because I think the situation is somehow reversed. There used to be a lot of skill in Arctic when the ice was thick, because the best way to have long-term predictability is also to have thick ice that you can thermodynamically predict where it's going to be there or not. So the predictability is maybe decreasing in the Arctic, and the difference between Arctic and Antarctic, even if you have the same thickness on average, would be the role of the ocean. I think the Arctic surface is much more isolated to the ocean than the Antarctic. So all the processes that I was trying to explain with the storage of surface conditions at depth that can re-emerge in the next winter, or even in the next summer, I'm not sure they will be that strong in the Arctic because it's so stratified. There are some mechanisms of re-emergence with the Arctic also that have been discovered, but I'm not sure they will be as strong. So I'd say it's, yeah, it's maybe more, I'm not sure it's going to be that strong in the Arctic. Or it depends maybe on the region, I don't know.
Maybe one last quick question. Yeah.
Hi, François, thanks for the nice talk. I was wondering if you keep information on the dynamical models, which CI's dynamical core they use, like VP, EVP, and if you can make, like if you can discriminate between the models and the performance with it.
I think most of those, they use viscous plastic or EVP approaches. None of them use any sort of anisotropic or MAB rheologies. So we didn't really discriminate the results within the dynamical models. What we did, it was one of my backup slides, but I can tell you is we looked at the integrated ice edge error, so this metric that penalizes the errors when you have a misplacement of the ice, and we stratified the results by dynamical versus statistical models, and the statistical models perform much better. So the dynamical models, they have sometimes the right area, but for the wrong reason, that they compensate the area, but the statistical models have a better geographical distribution of the sea ice area in general, concentration.
Okay, interesting, thanks.